Hi, everyone. Welcome back. We're going to continue our discussion of quantum mechanics today, and we're going to look at our third bound potential. This is the harmonic oscillator potential. This one is important for a variety of reasons. One is that there are a lot of physical systems that approximate a harmonic oscillator very, very well, such as the vibrational modes of molecules, or even the quantization of the electromagnetic field into photons. There are just a lot of systems that what we're going to find today applies to. The second thing is that this system has some unusual properties, which we'll discover as we go along. Okay, I'm going to turn over to the notebook now, and we'll get started. Okay, so far we've looked at two bound particle systems. We've looked at the infinite well, or particle in a box, and we've looked at the finite well, which we talked about last time. Okay? In each of these systems, we found energy levels, confined states. Okay? Which I'm just going to sketch in here. These two systems. Okay? In the case of the infinite well, the energy states are described by a simple analytic formula. The energy of the nth state is given by h squared over 8mL squared times n squared, where n is the quantum number for the state. Since the walls are infinitely high, there's no end to the number of states, and they're all described by this formula. For the finite well, things were much more complicated. We found that the energy had to be found by numerically solving an equation. For even parity states, the equation was tangent KL over 2 equals alpha over K. And for the odd parity states, we had a different equation, minus cotangent KL over 2 equals alpha over K. And these are implicit equations for the energy, but they're equations that have to be solved numerically. Okay? We also know what the wave functions for these systems look like. For the infinite well system, the wave functions look like the standing waves that we see on a stretched spring, which I'm going to try to draw here as well as I can, but they're very familiar to us. And in particular, they have nodes at the edges. For the infinite well, for the finite well, the wave functions look somewhat similar, but the wave function actually penetrates into the barrier. Which I've tried to draw there. By the way, these drawings I've just made, they're very useful and very common, but notice what I've done. First, I drew in the energy levels, nothing wrong with that. And then I went and drew the wave functions, but I drew them on top of the energy levels, okay? And that's a little bit weird because the y-axis is completely different for wave function and for energy level. For energy levels, the y-axis is energy, right? But for the wave function, the y-axis is related to the probability density. Also, each of these curves is offset from the other. Now, I've just done that because it's very common, and it's a very nice compact diagram that you get done with when you're done. But just keep in mind that for the wave function part, the position of the energy level is like the 0 for that particular sketch of the wave function. So that's the 0 for that one. This is the 0 for this one. This is the 0 for that sketch, and so on. Okay? And the two parts of the graph, the wave function part and the energy part, they have different y-axes. It's just a convenience that I'm drawing them this way. Anyway, sometimes people get confused by that. I don't want that to happen to you. Okay? Now, the system we're going to talk about today is called the harmonic oscillator potential, and I'll just sketch it right now. I'll do my best here. I was hoping the system would draw it automatically, but just give me a second. Okay, let's try drawing it one more time. I've drawn in some axes here. Oops. There we are. Pretty reasonable. Okay, it's easy to get carried away. In the harmonic oscillator potential, the potential energy is just parabolic in displacement. It's just 1/2 kx squared, where k is the spring constant for our harmonic oscillator. Okay, and x is the distance from the origin. Now, remember something about the harmonic oscillator. Harmonic oscillators have a natural frequency, omega, which is root k over m. And so we can turn this into an equation for k by squaring both sides and multiplying by m. So k is equal to m omega squared, okay? And it's very common to write u of x as 1/2 m omega squared x squared. And we'll probably do that, and we'll do that too. The reason for doing this is just in a particular system, it might be very hard to figure out what the spring constant is, but it might be easy to measure what the frequency is. So that's the tradition. Okay. And finally, because this is the resonance frequency, we'll give it a special name. We'll call it omega naught. Okay, very good. So this is the harmonic oscillator potential, okay? And to find the energy states of the harmonic oscillator, we should substitute into Schrodinger's equation and solve. And it's straightforward enough to do that. We then get minus h bar squared over 2m times second derivative of the wave function is equal to e minus u of x minus 1/2 m omega naught squared x squared times psi. And then we have to solve this differential equation. And this can be done. You'll get to do it in the advanced quantum mechanics course when you take that. And it can be solved by a well-known power series technique for solving ordinary differential equations. But in this class, we're not going to do that because we have to teach you the whole class on differential equations first. It doesn't seem like a good use of our time. Instead, we'll just look at the results, okay? Okay, the most important result is the result for the energy levels. There are quantized energy levels. E sub n is equal to n plus 1/2 times h bar omega naught. Okay, here let's put a box around that. There we are. So, excuse me. Okay, so we get quantized energy states. And look at these states. There's something interesting about them. They're equal to n plus 1/2 times h bar omega naught. Here, n, excuse me, Here, n is an integer, which can take on values 0, 1, 2, 3, and so on. So 0 is a good quantum number in this system. And if we sketch these out, they look like this. Even for n equals 0, the energy is not 0. Instead, it's 1/2 h bar omega. Here, I'll sketch that in. Okay? For the n equals 1 state, the energy is higher. That one I kind of messed up. 1 second. What's interesting is that these states are equally spaced. Okay? The spacing between any two neighboring states is just h bar omega naught. And the energy of the lowest one is not 0, but it's 1/2 h bar omega naught. Okay? So that's that's probably the most important result for the harmonic oscillator, is that we have equally spaced energy levels. When you solve the problem, you also find the wave functions, and I'll write some of these out too. But we'll have less to do with these. So psi 0, the lowest order, the lowest energy state, is equal to a constant times e to the minus alpha x squared. So can you see what the shape of this is? It peaks at x equals 0, which is in the center of the well, and then it's a Gaussian function. That is, it looks like a bell-shaped curve. Okay? Oh, something like that. Okay? Psi 1 is equal to another constant, we'll call it C1, times x e to the minus alpha x squared. Psi 2 is equal to another constant, C2, times 4x squared minus 2 times e to the minus alpha x squared, and so on. In fact, the nth one can be written this way. It's a constant. The constants all have to be established by normalization, okay, to figure out exactly what they are, times a function, the nth Hermite polynomial, times e to the minus alpha x squared. Now, the Hermite polynomials are not that well known to us, perhaps, but they're well known. They would be well-known functions to an analytical mathematician, particularly around the time that this work was done. So you and I might not know what they all are, but Mathematica has them all tabulated, for example, and so do most mathematical packages. They're a little exotic for us, but not very much so. There we are. And what do these look like? Here, let me sketch out the next few. Basically, they look like a Gaussian function times a polynomial function. So this one looks like, the first one we've just shown was a Gaussian times a constant. The next one is a Gaussian times a linear function. The third one is a Gaussian times a parabolic function. And so on. My drawings aren't so great, but you get the idea. Okay? Perfect. Here, let's stop here for a moment.